Ramanujan for G is now available on the Google Play Store. Try it out for free.
So we ended last class with by looking at waves, right? Now, one of the waves that we looked at was the sound wave, right? We ended with Doppler effect, if you remember, right? There are two other waves which we commonly know. Okay, one of the other wave is called the light wave, right? We will be looking at light waves in class 12. So I have a parallel class for class 12 students. There we look at light waves. We look at light waves in the context of electromagnetics. Okay, and of course, the same rules apply. The only thing with light waves is they have a fixed speed. C equals F lambda, and therefore, and they have a set of frequencies. Broad electromagnetic radiation has a broad set of frequencies. The what we can see is called visible light. And on either side of visible light, there is sorry, there's ultraviolet light. And then there's of course also higher frequency radiations which are used by things like the cell phone. There's also a kind of electromagnetic wave, right? Radio RF, right? Radio frequency, right? And on the other side, so coming back to light, right? There's the light wave, ultraviolet light, and on the other side there is what is called infrared light. Infrared light is also not visible. Okay, infrared light is emitted by bodies that are hot. Okay, what we know as, you know in many ways, like the sun's heat, etc., is arises due to the large body of infrared waves. Okay, so this is so this is so infrared, right? Happens on the other side um, uh, of the visible light, right? Infrared is actually also very, very important. So a lot of the wavelengths that are used in, say, solar panels, right? Typically they look to absorb a set of wavelengths which are light and which are partly infrared, portion of the infrared spectrum. The broader the spectrum that a solar panel absorbs, the greater the energy. Okay, so why am I providing all this background? Because we are now going to go into heat. Okay, this is class 11 class, so we are first going to heat. And one of the amazing things about heat is that we're going to look at thermal properties of matter first. Okay, so let me get started on that, and then we can kind of look at how to take things forward. Okay, so but before that, before we go to thermal properties of matter, let us briefly look at what is called the mechanical properties of fluids. Okay. Mechanical properties of fluids, I think you may all know, right? Fluids um, behave in, I hope you can see my screen. Fluids behave in certain ways, right? What is a fluid, right? As you know, solids, liquids, and gases are the three states of matter. There is a fourth state of matter called plasma, when when there are fused you know nuclei which are like kind of brought together. The electrons have all disappeared and they exist in a state of plasma. It is Plasma is very different from the plasma TV. Plasma is happens in in the sun. There is some relationship, but essentially plasma happens in the sun. you know and so at a very high temperature, matter transforms itself to a new state known as plasma. Okay. Now solids have definite shape and size. The atoms in a solid do not move. Okay. Notably, what does not move? The protons and neutrons do not move. You take a cell phone, keep it here, all the protons and neutrons stay where they are. Okay. Now when it comes to fluids, right? For instance, liquids, right? In the case of liquids, there is a certain amount of. So what happens to solids? You have heard of Young's modulus, etc. Right? There you can put stress. If you stretch it, then there is some movement, right? Otherwise, it does not. Its shape stays rigid, right? So when we look at mechanics, we largely look at rigid body dynamics. We say the body stays rigid, right? There's not work done to transform it. So if you, in a case of a ball, you pitch it, you drop it, it pitches little bit, it will change shape, but then it will come back to its original shape, right? So if you apply pressure, the change in volume is negligible. Okay. Now, now when it comes to liquids, on the other hand, they cannot take shear stress, right? Liquids, like if you heat it, there will be convection currents. You might have heard of all these cold currents in the water, right? There are all these kinds of movement inside a fluid that you do not see, inside liquid you do not see. There are, you know, atoms moving inside. Gases occupy a large volume. And you can change the pressure that you apply to a gas, and therefore its uh, mm, uh, PV equals constant, PV equals nRT. You would have heard of all these laws associated with gaseous material. Okay. So when you fill a automobile tire with air, the air does not go to the bottom, but it fills the whole space. So in that ways, a lot of these gases, they defy gravity, right? They have a speed that exceeds, that is able to overcome gravity. So they move around in whatever space you put it. Okay. So now if you pour liquid in a tire, it will go to the bottom, right? So liquids, they occupy the shape of the vessel, but then they also are very they accept gravity, right? They go to the bottom with respect to gravity. Okay. Since liquids and gases do not have specific shape, they can flow. Anything that flows, they are called fluids. Okay. Now you may have heard of this word shara. The word shara is essentially means flow. Okay. Shara, Sharavana, right? Saraswati. All these relate to rivers that flow. Saraswati River used to flow from, from the Himalaya, right? From the mountains of the Himalayas, and it did not flow like the Ganges into the Bay of Bengal. The Saraswati flowed into the was another river like the Indus. It flowed westward. Okay. And so Ganga, Yamuna, Saraswati mark the three great rivers that occupied, that were present in India. Saraswati became went underground after some time. Then people lived and they built wells, and they used to draw the water of the Saraswati. And even today, some people claim that there is a Saraswati. Anyway, there is another state of matter which happens at very, very large temperature. This state of matter is where the electrons are stripped from the outermost shells. They acquire a charge and are ionized particles, and that is called plasma. We already discussed this. Okay? So some scientists consider colloids as another state of matter, you know, which are suspension of tiny particles in liquids such as milk, should be considered a separate state of matter. So, like for instance, I don't know if you have had this um, saffron milk, right? Saffrons will be all over the milk, right? So they are talking about such colloids. Now, the air we breathe is fluid, right? The human body mostly consists of water, which is a fluid. A lot of processes, the human body, right, are mediated by fluids such as water. Solids have a definite shape, right? Because the intermolecular force of attraction is very large, right? The intermolecular force of attraction in liquids is small, but it is not negligible. In gases, there is very little atomic forces, so they kind of move around in in ways. And when you look at the kinetic theory of gases, it provides a model for how gases, ideal gases, behave. Okay, so a block of wood or iron is heavier. Block of iron is only heavier. Right? You know this, right? So now, and what makes something heavier is what is its density. Density is known as the mass per unit volume. Unit of density is kilograms per meter square. So density of solid, liquid, and gases. So iron has a high rho. Liquids have a slightly more decent rho, and gases have a very low rho. Okay? So for the above table, it is seen that the given density of liquids is one order of magnitude less than the solids. So what is the mass of a lead sphere of radius zero point 0.5? Right, rho times V. Right, and so rho is the density of lead, and V is if you have a lead sphere, what is the volume? 4 by 3 pi r cubed, and therefore you end up with a total mass. So with that, I'm going to end this section, and I'm going to move on to next to discuss what is called various forms of thermal properties of matter. So when we discuss thermal properties of matter, um, all right. So heat and temperature are two different things. Okay, heat is a form of energy. Okay, while temperature is is a measure of how hot something is. Okay, like for instance, my body temperature typically is 97.4. It is probably a little lower than yours. When I was young, my body temperature was 98.2. Now it is 97.4. Typically, some days it's less, some days it's more, but in the 97s. Okay. No, some people have a hotter bodies, 98.4, maybe even higher. Young children even higher. Okay, then when you get a fever, your temperature goes up. Right now, and it is used as to measure if you are sick. Right now, what is temperature? Right, so temperature is actually a measure of how fast the particles kind of vibrate. They stay in one place, but they kind of vibrate a little bit. So the commonly used property is variation of the volume of a liquid. Right, so how do you measure temperature? Right, you measure temperature by, if you place something in contact proximity to something that's hot, particularly a liquid, the liquid will expand based on its temperature. Lower the temperature, smaller the liquid. Higher the temperature, higher the volume. So based on that volume, you then get a measure of temperature. Okay. Now, so coefficient of what is called linear expansion. But before that, what are different measures of temperature? First, there is the centigrade. In India, the common measure of temperature is centigrade. Where I live, the common measure of temperature is called Fahrenheit. Okay, Fahrenheit is different from centigrade. Okay, now centigrade typically goes, from 0 to 40. They will say 40 degrees centigrade, 44 degrees centigrade. 44 degrees centigrade is a very hot day in India, right? But these days, it is very difficult to tell, But typically, 44 is a steaming day. You should be careful to go out in the hot temperature. You can get heat stroke. Okay? Take water, drink, and take an umbrella. Best way to deal with temperature, with the hot temperature, is to carry an umbrella. Okay. Now, the second scale is called Fahrenheit. Fahrenheit is like this: 0 degrees centigrade equals 32 degrees Fahrenheit. What is 0 degrees centigrade? It is the temperature at which, in under normal temperature and pressure, ice freezes. What happens to ice? Ice gets completely converted from what is freezing. Ice gets completely converted from liquid to solid at a fixed temperature. That temperature is 0 degrees centigrade, right? And or it is 32 degrees Fahrenheit. Now the temperature, now each degree of centigrade increase is 1.8 degrees of Fahrenheit increase, or 9 by 5. Okay. So if you wanted to convert from centigrade to Fahrenheit, right, what do? You you take the centigrade value, okay, you multiply it by 9 by 5, and you add 32. 32 plus 9 by 5 TC. Okay, 32 plus 9 by 5 TC equals TF. But let's write that down. Okay, so let's write that down. TF equals 32 plus 9 by 5 TC. Okay, so now when we look at the next one, right? When we look at the next one, when we convert from, there is another scale which is called the absolute scale, or Kelvin scale. Okay, so what is this Kelvin scale? The Kelvin scale has the following, right? The lowest temperature that anything can record in centigrade is minus 273.5 degrees centigrade, and this is called absolute zero. Okay, so when you are in absolute zero, what can you not do? You cannot at absolute zero, pretty much all activity comes to a perfect standstill. Okay, absolute zero is cannot be really attained. You can reach close to absolute zero, but it is the coldest you can get. Okay, coldest anything can get is absolute zero. Now zero is minus 273.5 degrees centigrade. Okay, so 0 degrees centigrade is 273.5 degrees Kelvin. So when we say 27 degrees is the normal temperature, that is roughly 300 degrees Kelvin. Okay, so if you are 30 degrees, it is 303 degrees Kelvin. Nobody reports, the daily temperature in Kelvin, because it's essentially a tool used by scientists. Okay, so now let's go on to the other ideas. Okay, now there is what is called the ideal gas equation, which is PV equals constant, right? Which comes from PV equals constant, which is Boyle's law, and then Charles' law, V over T equals constant. So you combine the two, you have PV equals nRT, which is the ideal gas equation, where N is the number of moles R is the number of R is known as the universal gas constant, 8.31 joules per mole per Kelvin. Okay, so 8.31 is R, right? PV equals nRT. Remember, PV equals nRT. So keep that in mind. Pressure times volume equals number of moles times universal gas constant times T. T is the temperature in Kelvin. Temperature is measured in Kelvin. Please note that fact. You do it in centigrade, everything will be wrong. Note this K. That is Kelvin. PV is what? Pressure times volume. The product of pressure and volume will give you joules. Okay. Pressure is what? Newtons per meter square. Okay. Pressure is, you apply pressure on something, is newtons per meter square. Right. Now, newtons per meter square times meter cubed will give you newtons per meter square times meter square will give you what? Newtons, right? Newton times extra meter. Newton meter is what? Joule. Okay. So PV is joules. So joules per mole per Kelvin is R. Okay. So remember the how we do this. Remember kelvins. Okay, PV equals nRT. PV is a very important formula. Please note ideal gas equation. Whenever they say ideal gas, you must know use PV equals nRT. Okay. Now, thermal expansion. Most objects, when you heat it, it will become bigger. Okay. Metallic lids, right? If when you have a metallic lid in a glass, you put some hot water to open it, right? Now, balloons will shrink when you place it in ice water. You may have seen it, right? These are all the tricks that children play. Learn about science. Enjoy such games, right? Thermal expansion is an increase in size when there is an increase in temperature. This V over T is a constant. More the V, more the T, right? So thermal expansion. All right. So now, if something increases in length, we say it is linear expansion. Something increases in area, we say it is, and we have a corresponding coefficient of areal expansion, right? So it's like that, coefficient of linear expansion, right? Now, how are these actually related? Typically, if the coefficient delta L over L equals alpha times delta T, note this formula, okay? dl by dt is alpha times L, where alpha is the coefficient of linear expansion, okay? So, so you remember that this is a dl by dt is alpha L. Now, dA by dt is 2 times alpha L times A. Okay, so the coefficient of areal expansion is twice the coefficient of linear expansion. The coefficient of volume expansion is 3 times the coefficient of linear expansion. Okay, so and so here you can see coefficient of volume expansion looks somewhat like this. Okay, so this is for copper. Okay. Now, water on the other hand has a special property. It does not follow this process. Water has the highest density. So what does this mean, right? The density declines as something is heated. Its volume expands, right, and its density declines, right? Now, water, on the other hand, as it's heated from 0 degrees, like it is frozen, right? So from 0 degrees, it first becomes more dense, and this is called the anomalous expansion of water. First becomes more dense, then it becomes less dense. As you heat it more and more and more, it will expand, like just like anything else. Okay, so that's how water behaves. Okay, so coefficient of volume expansion for gases, as you know, PV equals nRT. Therefore, you can then use that, right? Delta V is equal to delta V over V times 1 by delta T equals Therefore, you have for ideal gas, delta V over V equals delta T over T, right? So P delta V equals mu R and N R times delta T, right? So if you keep at constant pressure, the more the volume, the higher the temperature, the more the volume. Okay, at constant. Now, so we already showed this, right? The coefficient of y is the coefficient of volume expansion. V is equal to L cubed, right? So now delta V is what? V plus so delta V is what? 3L square delta L. V equal to L cubed. dV by dL is equal to what? dV by dL is 3L square delta L, right? Therefore, delta V over V equals 3 times delta L over L. Delta L over L is what? That is your coefficient of linear expansion. So delta V, AV, coefficient of volume expansion is 3 times coefficient of linear expansion, right? Delta L over L, how do you measure? That is, you can measure it using Young's modulus, right? We already discussed that linear stress over strain, right? So one form of stress is what is called thermal stress, right? When, let's say, you have something which is held in place right now, let's say, the temperature increases, right? When the temperature increases, these things push against each other, and that causes stress, that stress is called thermal stress. So what is the measure of that? Delta L over L. So delta F equals A times Y times delta L over L. Stress over strain is Young's modulus, right? So what is this delta F over A? That is your stress. Delta L over L is what? Strain. Okay. So now let us go on to the next topic, right? So dq by dt, right? Delta Q by delta T is called the heat capacity. The more heat you provide to a body, like you would have seen your mother take a pot of water and heat it in a gas stove, right? So you put it on the gas stove, then heat it up. So delta Q by delta T equals S, where S is the heat capacity. Now, heat capacity is the mass. Also, you can have specific heat capacity, which is the heat capacity per unit mass. So you have m times little s equals S. Okay. So using that, you can then have, or you can have molar heat capacity. Okay. So all these are very important ideas. Now, calorimetry, contraption of our system in which heat measurement can be done, is called a calorimeter. It's a wooden jacket inside which insulating material like wool is kept. There's a metallic material with water thermometer is inserted. Calorimetry is a means by which heat content is measured. Gold sphere of zero point 0.1 kg is placed for sufficient time in a vessel containing boiling water. Here's an example. So this is calorimetry, right? So in most of these questions with calorimetry, there is a contraption called a calorimeter. What is the calorimeter? It is a isolated um, container in which, with a thermometer, in which heat loss and heat gain is measured. Okay, you can use the thermometer to touch all the items there. And what typically happens is, when a hot body is in touch with a cold body, heat is transferred from the hot body to the cold body, and therefore heat lost is equal to heat gain. And so we already looked at m as theta, right? Theta is the change in temperature, or m as delta theta, right? M as delta theta equals the heat, delta Q, and heat is measured in joules. Delta Q equals ms delta theta, right? So a gold sphere, as we said, right? It is then immediately transferred to, gold sphere is placed for sufficient time in a vessel containing boiling water, so that it is at 100 degrees C. It is then immediately transferred to zero point 0.2 kg calorimeter, right? Containing 0.25 kg water at 20 degrees. Temperature of water rises and takes a degree of state of 25. Calculate the specific heat capacity of aluminium. So how do you find? So change in temperature of the gold is 100 minus 25, right? 75 degrees. So you take ms delta theta for gold. Its weight was zero point 0.1, or mass was zero point 0.1. So zero point 0.1 times S of gold, specific heat capacity of gold, times delta T. Delta T is 75 degrees. That is the heat lost, right? And so what is the heat gained? The heat is gained by the calorimeter, right? The calorimeter has gone up 5 degrees. What is its weight? Zero point 0.2, right? So zero point 0.2 times SCU, right? Plus there's also the water, right? So water also gains 0.25 times S times 5. So it went from 20 to 25 degrees. So the pot gained some heat, and the water gained some heat. Total heat gained is the heat lost by the gold, right? So heat lost equals heat gain is basically what you do: ms delta theta, ms delta theta, ms delta theta. Okay, so calorimeter problems all deal with that. Okay, so change of state from solid to liquid is called melting. Change of state from liquid to solid is called fusion, right? And the point at which something goes from solid to liquid is the melting point. Regelation happens when there is a refreezing due to the removal of pressure, like how it happens in skating. Remove pressure, suddenly things will freeze. Okay. Vaporization is when something goes from solid to vapor, liquid to vapor. Solid to vapor also can happen under different types of pressure, right? But most often you go from liquid to vapor. The temperature at which liquid and vapor coexist at Vietnam is called the boiling point. We looked at freezing point or melting point, right? We looked at melting point. Now we are looking at boiling point, right? Boiling point is the temperature at which something converts from liquid to vapor. Under normal temperature and pressure, it is called the normal boiling point. If you put some pressure, things will change. As you know, PV equals nRT. Now, they always provide this what is called a phase diagram. Phase diagram typically looks at phase transitions with respect to pressure and temperature. Okay, so now it is a pressure versus temperature curve. What is a phase diagram, sir? Pressure versus temperature curve. So if you had, let us say, a particular substance, right? Or like say water, right? Now each of these it will behave slightly differently, So at in this area, right? It goes from, this is vapor, this is solid. So it goes from solid to vapor under certain substance. But most things like particular water vapor goes from solid to liquid to gas as you heat it, right? If at this temperature, solid to liquid to gas. Okay, now there is also this what is called supercritical fluid. Okay, supercritical is a very important term. Compressible fluid is when you have a lot of pressure, increase the pressure a lot, right? Now if you have compressed fluid and you keep heating compressed fluid, you end up with a supercritical fluid. Now, supercritical is a very important word because where do these things matter the most? They matter the most in the transmission of heat in, say, a thermal power station. So, what is a thermal power station, right? A thermal power station is something that generates electricity. You will learn about a little bit about motors and what is called generators. You learn about generators in the in class 12. We have just now completed some of those sections with class 12. Okay, now what I want to explain is that if you look at this phase diagram, right, supercritical fluid matters in the context of a power plant, thermal power plant. A thermal power plant, supercritical fluids can be used, and they will be used to transmit the heat, and to drive the turbines. Okay, so in a hydroelectric plant, what happens? The force of water from falling water runs the turbine, right? You would have seen, right? If you go to near a dam, you will see this hydroelectric power being generated by generators spinning when water falls, right? Now, in a thermal power plant, coal is or natural gas is burnt, and this produces heat energy. This heat energy is then converted to electricity through the use of some kind of fluid. It could be water vapor, right? Or supercritical, some other kind of fluid. Okay, fluids will convert heat energy to, because fluids move under high temperature, right? So the aim is to convert heat energy generated typically by a fossil fuel in a thermal plant into electricity. And that is done by taking that heat energy and then driving a mechanical system to produce electricity. So convert it to mechanical, then mechanical to electricity. Now, latent heat is what happens when at the boiling point or at a freezing point, right? What happens is the amount of heat is added, and then the body changes state. So Q is equal to M times L. So if you have a certain mass, it will have a latent heat of fusion or latent heat of vaporization. Q is equal to LF times uh, M, or Q is equal to LV times M. Okay, so that's how these things work. Okay, now again, this latent heat also leads to heat loss equals heat gain kind of problems. So heat loss by water equals heat gain by ice. When something is, let's say there's a glass of water, you put in an ice, the ice is melting, it goes, and then it then also reaches the temperature of the water, right? So you have both ms delta theta as well as ml, because the ice has to melt. When the ice is melting, it will go through ml, and then ml plus ms delta theta will equal to the temperature of the water that rose up. Okay, heat loss equals heat gained. The ice gained heat from the surrounding water, and it became water at the same temperature that was as the surroundings. So they reach a equilibrium that is in between where it was. Okay, so you have some unknown. You say there is some equilibrium temperature that you don't know, right? And that is the temperature at which the whole system will reach. Okay, now let us look at conduction of heat. Just like we all know of conduction of electricity, right? What conducts electricity? Metals conduct electricity. The same metals are also good conductors of heat. Okay, so conduction of heat, what happens? You put heat at one end, the whole rod will become hot. If you have touched, I don't know if you have touched a hot piece of metal, hand will, because it's the whole rod will be hot because it's a good conductor, heat conductor. Ka, right? The heat is given by K times A is the area, and 1 by L. SL over A, you would have heard, right? So Ka times Tc minus Td, that is the difference in temperature. Okay, so how quickly a temperature difference reaches, right? You have what is called the heat conductivity, Ka delta T by L. Okay, it's directly proportional to A and inversely proportional to, all right. So now here you have right, delta T over L, right? An iron chain is and a pendant are welded together. The iron chain is at 400, the pendant is at 300. What is the temperature of the junction? You have an unknown, which is the temperature of the junction, but you will end up with H1 equals H2. What is H1 and what is H2? It's called the thermal conductivity, right? So the heat conductivity, delta T over L, Ka delta T over L equals Ka delta T over L. So the Ks are different. In this case, the areas of the wires are different. A is the area, L is the length. Okay, Ka delta T over L, Ka delta T over L, H1 equals H2, right? So we looked at convection. Convection happens through the actual movement of liquids and fluids. Like typically in liquids, you have convection currents, right? We talk about convection currents in the ocean. In air, you have also certain types of flow of air. There is also convection. There's a actual movement in, and for instance, the Earth's rotation modifies certain currents. Also, notably, the atmosphere. You have a wave in the heat wave, cold wave, etc. These are all heat convection currents in the atmosphere, right? So, radiation is a third type of temperature. Okay, when there is free space, you have what is called infrared radiation, which goes infrared light or other electromagnetic waves are transmitted across distances. The sun emits so much heat. Why is it so hot in the daytime? There is light, but there's also heat, and that heat comes in the form of invisible light known as infrared light. That is also transparent and falls on your body and makes it hot. All bodies with temperature radiate energy. All hot bodies radiate energy. It is given by what is called Stefan Boltzmann law, right? And so the heat is proportional to the surface area times sigma times T to the power 4, where T is the temperature in Kelvin. It is the fourth power of the temperature, T to the power of 4, A delta T to the power of 4. Okay, Wien's displacement law, lambda m T equals a constant. Okay, so now if you have a surrounding temperature, T to the power of 4 minus T to the power of 4 will give you the heat loss equals heat gain, right? So if you have a surrounding temperature, that will have a T to the power of 4. The hot body will have a T to the power of 4. So you'll have T to the power of 4 minus Ts of 4. Okay. So this is all the material. Then let me discuss finally greenhouse effect. Greenhouse effect works like this. The sun radiates tremendous amount of infrared heat, as we discussed, given by H equals A sigma T to the power of 4. So the sun is a black body. Okay, it radiates heat, tremendous amount of heat. It is in thousands of degrees of centigrade. You and I live in 30 degrees centigrade. This is in the thousands. Okay, now the heat of the sun, which radiates so much heat, falls on the Earth's atmosphere. The Earth's atmosphere tends to absorb that heat. There are certain gases in the Earth's atmosphere which absorbs the heat. Otherwise, what happens? It comes, hit the surface of the Earth, and goes back. Okay. Sometimes some of it hits the surface of the Earth and is reflected back. Like for the light, some of it is reflected back from the Earth, right? But some of the infrared radiation is held in place in what is called a greenhouse. What is a greenhouse? Greenhouse is a glass covering with, and because it is glass based, light can come through. Okay, so in the greenhouse will become warmer and warmer and warmer as the day progresses, because the heat comes in and it stays inside. It is not radiated back. Okay, and what the CO2, methane, nitrous oxide, and CFCs, they are various gases in the Earth's atmosphere which get the heat and then hold it in place. Okay, so they say because of this, what is going to happen? The temperature, the lot of heat is being held by the by these hot bodies, by these gases, right? And these tend to raise the average temperature. And they say it will go up. It has gone up a point 7 or something. It has the last 40-50 years, it has gone up tremendously, zero point 0.3 or zero point 0.4 degrees centigrade, right? But they expect it to go much further. Okay, so finally, the last uh, point I'm going to make in this chapter is what is called Newton's law of cooling. the rate of loss of heat is directly proportional to the difference in temperature between the body and its surroundings. dq by dt is the rate of loss of heat. The dq by dt equals minus k times t minus ts. Okay, so now dq is what? ms dt, right? So what is this t? This is a rate formula. This is time. What is this t? This is a temperature. Okay, so dq by d small t is the rate of loss of heat equals minus k times t minus ts. T is the temperature of the hot body. Ts is the temperature of the surroundings, right? So now if you do write dq as ms dt and then you integrate, right, then you will have left hand side become ln, right hand side become kt plus c. And then the solution to this one, right, you can then write it in the, remember ln is what? Log to the base e. So you can write this as e to the kt, e to the kt, e to the minus rt times s equals t of t equals t env plus t naught minus t env times e to the minus rt, right? So this comes directly from this integration. Okay, but you can very well use this integration. Okay, see, if you at t equals 0, at t equals 0, you say this is t naught. What is the t equals 0? What is this? T naught, right? um, um, this is also t naught, right? Now at any t, what is the value, right? So that value will be e to the power of minus kt plus this one. Okay, and that formula becomes this formula. You can try it out here by yourself. Okay, but this is how this is derived, but you can also use this formula. Okay, so it is not good to memorize it, but to know how to go from here to here. Okay, so please try to derive this or look in a textbook where this is very well simply derived, or you can look in your Wikipedia. This derivation is there in Wikipedia. This leads to this. This is just a mathematical derivation. This is not difficult. Okay, so now oven cools from 90 to 80 in 2 minutes when the room temperature is at 25 degrees. How long will it take to cool from 80 to 70? Right? So one way to do this is to use this formula. Okay, so this formula, right, this one gives you one equation, T environment, right, 25, convert to Kelvin. Okay, T naught is what? 90, right? So um, this T environment is also 25, right? Remember, the environment's temperature is not going to change. Okay, so environment temperature is going to stay the same. So this, from this, when you plug this in, you will end up with calculating this R. Okay, and otherwise you can use what they have used. You can use this equation itself. Okay, now this equation, right, you can use the average temperature here, ms dt by t minus ts, right? So k times t2 minus tn, right? So what they do is they use an averaging formula for that. Okay, so I don't have time to go over this today, but I will go over this in the next class as to how he's using this clever method here. Okay, but generally speaking, if you can use this only, right, ms ln t minus t is equals kt, right, plus c, and at t equals time equals 0, this will go to 0. You end up with this formula as your corresponding constant, right? At t equals 0, what is this c constant? Then at any other time you can then calculate the value. Okay, so this is the surrounding temperature at time t equals 0. What was this value, right? T naught, this value will be t naught. What that will give you the constant. Okay, so from this you can then calculate the full-fledged equation. Okay, so use the boundary conditions of a differential equation. Right. So with that, I'm going to stop, and then we will continue our discussion next class. Okay. Thank you.